So we'll look at a final example of the pitfalls of lazy evaluation, which arises through the interaction between laziness and I/O operations. So we'll illustrate this with the following function, which I'll describe what it does. You give it a file name, it reads the file, converts all of the contents, all of the text in the file to uppercase and writes it back to the file. So this is a destructive operation on the file that you're going to modify, and it's called shoutify. Turns everything into uppercase. So here's what it does. You read the file and the contents, you then convert to uppercase by mapping the toUpper function on it to get shout. And then we're going to write the new contents back into the file, and just for the sake of being able to see what we've done, we'll also return that string as the result. So we get a string as the result of this operation as well as an actual operation. So let's try this out on the file below. Let's create a file to begin with so that we've got something to shoutify. So let me write file. I'll call it temp.text. So a temporary file, and I'm going to put in just a single word, hello. So that's the contents of my file. If I read that file, I can see that it does exist. And they're the contents. Okay, so now I should be able to shoutify my file. Namely, let me just make sure I'm completely up to date here. So let me save that and reload it. Okay, so I now should be able to shoutify that file, the temporary file, and we see what happens. We get an exception. The open file resource busy file is locked. Okay, so this is an operating system level error that is being propagated up. And what's happening is that in the operating system we can open a file for reading or we can open it for writing, but we can't do both at the same time. So that's an operating system level constraint. And so what happens is when we read the file, we open the file for reading. But because of lazy evaluation, we don't actually complete reading the file. Even though we're doing a map to upper contents here, we're not actually computing all of that. So that when we come to write the file, we haven't yet completed reading the file. So when you try and open a file for reading and then you try and write to it at the same time, you get an error, you get an exception. So laziness has really caught us out here. So how can we fix that? Well, the obvious thing to do would be to use our seek function to make sure that we actually compute this shout thing before we actually write to the file. So if we actually compute it, then the file will be read and everything will be great. So let's try that and reload that and try running it one more time. We still get an error. So where is that exception coming from? Why doesn't seek fix that? Well, the gotcha with seek in general, so this is a general thing, is that seek is still quite lazy. Seek can help us trigger the evaluation of an argument, but it doesn't do much evaluation. It sort of does the minimal amount of useful evaluation. It does something called evaluation to weak head normal form. So examples of weak head normal forms are, for example, anything cons anything, or a pair of anything you like. I used undefined to sort of emphasize that these are perfectly okay weak head normal forms. For example, if you do this, then the answer will be 3. The fact that this is undefined and this is undefined doesn't matter to seek, because seek doesn't try to evaluate that much. And so the problem is that all we've done by doing a seek is to cause the first cons of the output to be computed. So we're reading basically the first character of the file. That's all we need to be able to read. All we need to read to know that we have at least one cons in the output. So seek doesn't do enough work. So we can trick the system into doing a bit more work by, instead of first computing shout, we could compute, for example, the last character of shout. You can only compute the last character of shout if you've read all of the characters. You won't know you've read all the characters unless you won't know you've got the last character until you've really read to the very end. So if I replace this by last or length, for example, that's another trick I could use. I can force this to do the complete computation of shout, or at least to read the file fully. In this case, not the full computation necessarily, but at least fully read the file. So now, indeed, Shoutify will actually modify the text and convert it to uppercase. So if we go back and read the contents, we see that the contents is now the uppercase version. So one way to fix this is often to work with lower level operations. So read file and write file are actually higher level operations which embody, for example, read file means open the file for reading and then start reading, and then eventually you close the file for reading. So one possibility is to work with the lower level primitives to avoid these kind of errors. Another way, so that's all in system.io. The standard library for I/O contains all of the lower level operations, of which read file and write file are sort of higher level abstractions. But another way to do this is to use a strict version of the I/O operations, and this can be imported as, for example, this can be imported as system.io.strict. And if I, for example, imported it qualified, means it won't clash, the names won't clash with the existing ones, I could use a strict read file operation, namely the read file operation of the system.io.strict. And I could replace read file with this strict read file as an alternative, and I think maybe cleaner solution to doing this, what seems to be a bit of a hack to get this, this laziness fixed. So what strict read file means, it will read all of the file in one go. And that will prevent. That means that the file will be closed as at the end of this instruction in the I/O block. Okay, to conclude, I just want to say a couple of words about a place where we often do need to control evaluation, and that is to do parallel computation. Now, in theory, a compiler for a pure functional language like Haskell, and there aren't many pure functional languages. But a pure functional language has the advantage that computations can be freely reordered without changing the result, ignoring the possibility that you get non-termination. But in practice, it's quite hard for the compiler to choose the right places to do that, and you end up with too many potential things that you could try and compute in parallel, but you really need to do them in a smart way for that to be effective. So one of the key building blocks for really controlling the computation order are two combinators, two functions, which are a bit like seek. First one is called pseek, which is basically what we've been using seek for. So really, probably strictly speaking, we should have been using pseek in our examples. It gives a very strict promise that it will do left to right evaluation. First evaluate the first thing, then the second thing. We've been assuming that, but actually a compiler, if we turn on optimization, might actually reorder that. So pseek gives you a much stronger guarantee of what we actually want. But the other key ingredient is something called par. It has the same type as seek, but what it does is gives a hint to the compiler to compute the A and the B in parallel when possible. And so this can be used to structure a computation so that you make use of the multiple cores that your system might have. And in order to take advantage of this, you'll need the GHC-threaded runtime flag to allow the multi-threaded compilation to have some effect. So in a sense, this is also a control of evaluation, and lazy evaluation is the particular default evaluation. And these give ways of overriding that or controlling that and changing that, which are very useful in parallel programming. And as I mentioned earlier, there's a course all about that that you can enjoy later in your studies. So in conclusion, laziness is all about evaluate at most once for arguments. And it leads to a particular programming style which can be very elegant. You don't have to use laziness in any particular way, but it can be a powerful tool that can help you structure and make your programs more modular. But when it comes down to fine-grained details of performance, in particular space usage, it's really tricky actually to handle. And evaluation can be controlled to some extent by combinations of, for example, using tail recursion and strictness via seek. But you absolutely shouldn't be using this in your labs. This is really for more advanced programming and performance tweaking of finished systems, and not for code development.